So we're not going to look at how do these structures function to allow us to perceive sound. We're not going to go into the actual physiology of what's going on. We're simply going to look at how do the structures line up so that we can actually hear what we're hearing. And so what we're looking at here is we're looking at how do sound waves travel. And sound waves travel based off of what's referred to as a sinusoidal wave. So it's like waves that you see at the beach. When they strike the tympanic membrane, what it does is it causes this sinusoidal wave to turn into what's referred to as a compression wave, a vibration wave. The vibration wave is going to lead to vibrations through the ossicles, through the malleus, then the incus, and then the stapes, and then will lead to vibrations on the oval window. The oval window will vibrate, and as it vibrates, it's going to reconfigure that sound wave back to a sinusoidal wave through the perilymph. This perilymph sound wave will travel based off of the wavelength, wave height of the sound wave, which is going to be indicative of its frequency, through the cochlea, and then back out through the oval window, and then will dissipate through the middle ear and the auditory or eustachian tube. The way in which we perceive this sound, the way in which we actually register the sound at the cochlea is off of what's referred to as a tonographic map. And so we talked about having the topographic organization of the receptor field. In the case of the ear, this topographic organization is actually set up in a frequency-dependent fashion or a tonographic map. And so this tonographic map is set up in such a way that the highest frequencies are at the window edge, and the lowest frequencies are at the apical edge of the coil. And this has to deal with the wavelength of the sound and the amount of energy that we see within the sound based off of its frequency, where high frequency sounds have less energy within them than the low frequency sounds. Now we're able to perceive sounds from about 20,000 hertz all the way down to around 180 hertz of frequency. And that's our normal sound range. As we age, we start to lose the higher frequency sounds. And the reason why we lose the higher frequency sounds is because those are the areas that are constantly being bombarded by sound waves, regardless of the actual frequency of sound wave that we are hearing. So we pick up this sound wave, and this sound wave is going to get picked up. It's going to cause deflection on the hair cells, and it's going to cause the hair cell to go about sending the action potential signal. This signal is going to pass to the nuclei of the cochlear nerve. The cochlear nerve nuclei is then going to transmit information both contralateral and ipsilateral to the olive nuclei of the pons, which will then pass through the lateral meniscus into the collicus, where it's going to synapse again. It's going to then go to the geniculate within the thalamus, and then from there it's going to head out to the primary auditory cortex. Along this way, we can utilize that passage of information to be able to determine where in the world a sound happens to be coming from without actually needing to see where the sound is coming from. This is where we can do what's referred to as echolocate or tonal locate where a sound happens to be. And it has to deal with the fact of what's referred to as a delayed response in the signaling pathway. And so there's a slight delay in between sounds being heard on the right versus sounds being heard on the left based off of where that sound is within the world. And when we get the convergence of the relays within the olive nuclei and within the lemniscal nuclei, where we get the two signals converging together on each other, we get the maximum rate of action potentials. Where we get inhibition of the signal, meaning that we're in a refractory period of time, we lose the ability to converge and we get the weakest amount of signal. And based off of where those neurons happen to be laid out within the olive nuclei, we're able to perceive where sounds happen to be coming from within the world. And so if we look at it, where the red and the green line up, where we have a 50-50 split, we know that, okay, that is where specifically in 360 degrees around us in all planes of the body, that's where that sound happens to be. And as that sound changes its location, that convergence point will change within the olive nuclei in all planes of the body in all 360 degrees. And so based off of the rate of excitation versus inhibition coming from the olive nuclei, we can sit at a stoplight and hear a siren coming and know it's a fire truck siren and it's coming from behind and to the right of me. So I know, okay, I need to make sure that I am freeing up traffic by moving in a certain direction without having to look around for where that sound happens to be coming from. Once the sound waves get passed through the pathway, ignoring the convergence and divergence of signals from the olive nuclei, it's going to head to the cochlea. And in the cochlea, we have what's referred to as the primary auditory cortex. The primary auditory cortex has a tonographic map that is the exact same map that we see laid out within the cochlea, which means that if I am a hair cell at 200 hertz, the neuron I am synapsing on is going to go to the 200 hertz area of the primary auditory cortex on both the right and left temporal lobe. From that primary auditory cortex, it's then going to get sent out into the secondary auditory cortex, which will then mix and match frequency sounds together so that I start to build sound waves on top of each other to make a harmonious sound from that. I don't actually understand what the sound is at that point in time, but at least I can start to compile sounds together. The compilation of sounds together and my ability to perceive sounds is based off what's referred to as a forward mapping and inverse mapping pathway. The forward mapping and inverse mapping pathway allows me to understand and replicate the sounds that are coming from the environment to me. It allows me to learn what sounds happen to be. It allows me to learn what sounds happen to mean. These areas that we see within the cerebral cortex coordinate with Wernicke's area, area 40, and Broca's areas, areas 45 and 44, along with what's referred to as the belt pathway or the striated pathway. This area is what's going to allow me to understand and replicate sounds, produce sounds, and understand what sounds need to be produced. This is the same area that gets disrupted when people who have dyslexia come into play. This is the same pathway that gets disrupted for people who have who fall on the autism spectrum disorder. This is the same pathway that gets disrupted for people who have stuttering issues. This pathway gets laid out in such a way that we have a feedback loop that gets developed that allows us to be able to vocalize correctly and time pattern our speech correctly so that we can understand not only what we need to say, but understand what is being said to us. The same pathway comes into play when we are looking at non-verbal vocalization cues, what we usually refer to as facial expressions or non-verbal communication. And this is where we get a link in with limbic system structures, as well as prefrontal structures, as well as frontal cortical structures, along with the areas associated with Broca's areas and Wernicke's areas. And part of this vocalization feedback loop that we have is one of the issues that comes into play for people who aren't used to speaking in front of audiences, where when they are on an amplification mechanism, there's a delay in when they are talking versus when they are hearing their own voice. And that small bit of delay can disrupt this overall pathway, leading to a poor speech pattern for people when they first start speaking to a large audience. The same pathway gets disrupted for people who have stuttering issues, where the somatosensory pathway and the auditory processing pathway are not matching the vocalization pathway in terms of the feedbacks within those patterns. And when the rapidity of speaking, when the rate of speaking increases, it gets even more dysregulated. And when that pathway gets even more dysregulated, the stutter becomes even more pronounced. This is what happens when people who have stuttering issues have worse stutters under periods of stress.